Hello, this is Lilou. I'm in Paris and I'm so excited to have one of my favorite guests, Nassim Haramein. Hello.
Hello, it's so good to see you again.
How are you?
Great.
You look like you're doing fantastic.
Oh, thank you. Yeah, I feel fantastic.
So much has been going on lately, and I've interviewed you back then in Hawaii, in Kauai.
Yes.
You had just
years
surfed
ago.
this amazing wave at that time.
Yes.
And you have been doing so much, and now you live, in France, Switzerland. I mean, we see you around Europe more and more. You have changed location.
Yeah.
A lot has been going on. You have released a paper a year ago. There is a new one coming up. I want to discuss about all that. All your research, you're known as this physicist, and everybody wants to know where you're at, of course, and why all this is taking so long and what's going on.
Yeah.
And it's very exciting, lots of things to talk about. So first, let's talk of this 0-point energy. I want to know all about it and what can we expect from it in the near future.
Yeah, I mean, there's like the history of 0-point energy is really a little bit confused, even in the mainstream scientific community. And even if you ask ChatGPT, which is a good indicator because it's using what's been published, there's confusion about the source of 0-point energy, the history of it. Tendencies to say 0-point energy is the result of Heisenberg uncertainty principle, and that's actually wrong. And so the paper I just published a year ago starts with the history of 0-point energy because I wanted to put everything back square and clear and in order. Exactly. 0-point energy comes actually from the first equations in quantum mechanics. And it's the result of Max Planck trying to make a better light bulb. He was asked by the Bureau of Standard to make a better element for the light bulb. And so he had to solve equations that are thermodynamic equation, like the little filaments heat up and they emit electromagnetic fields, right? That's how the lights used to work. Now they're diodes, they're a little bit different. But they used to have a little element that would burn eventually. And so he was trying to make a better one of those. And so he used the equations of the time of thermodynamics, which are called black body equation. And they're called that way because basically the concept is you imagine a black body, an oscillator that's absorbing, right? Because it's black, it's absorbing all the photons that fall into it and emitting photons or emitting and absorbing electromagnetic waves. At the time, they didn't have photons. That came as a result. But, he was right. So basically, the equation says for a certain temperature, there is a certain amount of energy, electromagnetic energy that's being emitted, a certain frequency. So, hotter, higher the frequency. And the equations at the time were saying that when it got really hot and got into the ultraviolet frequency, that it would emit infinite amount of ultraviolet. And that's not what they were measuring in laboratory. So to make a long story short, he basically came up with a fudge factor. He put a fudge factor in the equation. He didn't think it was very elegant. He didn't like it himself. But he said, this is the only thing I can figure out that gives the right answer. So he put the fudge factor in. And that became Planck's constant. He called it H. Eventually it became H bar. And basically, so to be clear, so he's describing a little bit of an oscillator. And this is another thing that's not taught clearly. So let's, during this interview, I'd like to rectify a few things.
Yes.
Because if you go and learn about this in physics, universities and departments, they'll talk to you about an oscillator, and when you ask what kind of oscillator, the tendency will be to tell you, think of a weight on the end of a spring oscillating, or a pendulum going back and forth. But the universe doesn't make springs with weights on it. right? That's not what it's making when it's making the world we live in. It's not I mean, it's making springs and weights, but after it made the human that made the spring and the weight, right? But if we're trying to understand the universe, if we're trying to understand really like how it works, then if we're describing the mass of an oscillator, the oscillator should be something that's spinning. An oscillator that's spinning, a little spinner, a little like, you know, a little top, or, you know. And because everything we see in the universe is little spheres that are spinning. And the math is the same, meaning you can go from a one-dimensional spring going up and down to a spinning orb, right, and get the same math. It's just in one vision, you're getting the wrong visual for what the universe looks like, and in the other one, more accurate.
But this
visual.
has been removed deliberately, or?
Well, it's
without
just,
going too much into that, but what has been
it's
going
the
on?
problem of using analogies in physics. If you use the wrong analogy, you can get the wrong mental picture. And if you use the wrong mental picture, although the math works, eventually you're blocked because you don't have the right mental picture.
You can't go any further,
You can't go any further.
Yeah.
So you get this kind of thing. Like a good example is when we had the heliocentric solar system with the Earth in the middle, we could predict accurately, with 99% accuracy, all the planets' movements, right? But when we looked at the solar system, it looked like a bad hair day, right? But the math worked, right? But we had the wrong model. And as soon as we put the sun in the middle, everything cleaned up, and then it got more accurate, and then we could move on from it. So basically, this is the danger of having you can get the right math with the wrong model. And so to carry on, basically at the beginning of the paper we make that statement. We're not talking about a spring with a weight, we're talking about a spinner, so that we understand that spin is involved. And the free parameter, or the fudge factor that Planck added, was this h bar, made it so that the spin, the angular momentum of the little spinner, was quantified, like it's a quanta of energy. And that he didn't like, because it was like, it meant that the little oscillator, it was emitting packets of energy in the electromagnetic field, that the electromagnetic field was quantized. And that was the start of quantum theory. And eventually Einstein said, oh, those packets are probably the little packets that are knocking the electrons out in the photoelectric effect. So he wrote a paper on this and got the Nobel Prize for it. So he didn't get the Nobel Prize for relativity, he got the Nobel Prize for actually, you know, some of the first equations of quantum mechanics. But
all this is important to say.
Yeah, it's important to understand. And so and the part that's not really well understood neither is that as Max Planck, so he wrote his first equation for the black body radiation and put H in there and got the right answers, right, for the spectrum of light in the 1900, right? So the year 1900, he wrote this equation. By 1912, he had tried to figure out what these equations were saying about the energy of the oscillator, like the internal energy of the oscillator, right? The way the oscillator is emitting and absorbing photons, but as well like its internal energy. And when he was writing those equations, there was something weird that happened to his graph, which was frequency against temperature. When he put the temperature of the equation at 0 Kelvin, which is super cold, right? It's like it's minus 270 some Celsius, right? It's seriously cold. Well, where the oscillator should be frozen, there should be no thermal emission, there should be no thermodynamic electromagnetic radiation. Well, the equation said that there was an infinite amount of energy. And that's why he called it 0-point energy. At 0 Kelvin, there is still oscillation, there's still energy. The thing, you can't reach 0 energy. It doesn't get there. It always has energy, and the mode of oscillation go towards infinity. The equation diverges to infinity. There's an infinite amount of energy at the ground state of the electromagnetic field.
So what's the implication of that for us as human beings?
Well, you know, if I would have been Max Planck and I would have found that, I would have thought, wow, I found the energy at the base of creation.
Limitless.
Limitless. All creation must come out of this field of energy. It's unclear exactly what happened. Einstein and Otto Stern worked on it and all this, but you know, I think, and you know, I'm not a conspiracy theorist at all. I'm not, like, I always tend to give the benefit of the doubt to everybody. But from all the research I've done, it becomes kind of clear, and certainly in the later years, that at that time, you know, you had like the First World War and the Second World War, and there was a lot of research being done to like make better bombs and atomic bombs and all this. And the idea that like there'd be a field of infinite amount of energy or extremely high density energy that you could tap into might have not been, you know, the thing that was like wanting to be promoted. And so I think in some certain ways it got censored, and that like actually, you know, there was deliberate, later on, there was deliberate distractions that were added to physics to direct physics in another direction. And there's actually an interview of Oppenheimer with a French physicist in French, because Oppenheimer spoke French. And it's a great interview because he's talking about censor in physics at the time. This is in 1957, I think that interview was done. And the French physicist that was there mentions, you know, that how difficult it is to move forward in physics with all the secrecy and the black budgets and all this. And that even things like, at one point, he blurs that out. It just blew my mind. I had to rewind a few times because I couldn't believe he said that. But he looks at Oppenheimer and he says there's even censor about the gravitational constant. And, you know, the gravitational constant is known since, you know, since Newton. And like, you know, many decades before, and so and everybody thinks we know everything about the gravitational constants. To say that somehow there's even censor of the gravitation, something about gravity anyway, has been censored. This is very, very remarkable. I think it's a great interview. Maybe we can put it in the link, you know.
Sure.
But so eventually 0-point energy becomes this background thing, and eventually it's associated with uncertainty, Heisenberg uncertainty principle, which states that we never know the exact position and momentum of a particle, that like there's an uncertainty in our equations, in our capacity to identify where a particle is or where it's going. And you know,
well, why is there nobody else before you that has looked at this and kind of went towards solving the solution and putting it back on air, let's say?
Well, there's been many people that tried, but zero-point energy got a really bad rap for most of modern physics. You know, in general, what happened is that instead of going, we found the source of life, or we found the source of the universe, they went, how do we get rid of this infinite amount of energy? And so they wrote the equations so that all the waveform of the zero-point energy would cancel out perfectly, symmetrically, so that it'd be zero, so that you could ignore it. So in general, students were told, it's not anything you can use, it's not anything that does anything, just ignore it. And so they zeroed out the zero-point energy. So in the paper I published a year ago, we go through formally the equations of quantum mechanics, and we show that by zeroing out the zero-point energy, you actually make all the foundations of quantum mechanics unstable, meaning the equation become inconsistent. It's not to be too technical, it's called the equation becomes commutative when they should be non-commutative. And let me explain what that means. Remember, we're describing a little oscillator that's spinning and absorbing photons and emitting photons? Well, when you remove the zero-point energy, remember he was trying to find the internal energy of the system? It's like you remove its source of energy. So now you have an oscillator that has no source. And so if you calculate, the thing should stop oscillating, you know, very, very quickly because it has no source of energy.
Yeah.
So basically, what they've accused people that work on zero-point energy and certainly on technology that extracts energy from zero point, that they're trying to violate the laws of conservation of energy, they violated the laws of conservation of energy in their own equation, both at the quantum level, just the way I told you. They've made an oscillator that's magical, that has no source of energy. And at the cosmological level, when they start with a big bang that took its energy from some miracle moment and there was a bang. Right,
but it's interesting because you are actually, I don't know how associated you are with the CERN, but they have done a lot of tests about that. So are they open to all of this?
Well, I was invited to present at CERN in 2013 after I predicted correctly the radius of the proton, which the standard model was wrong by 4%. And but then the director at the time found out that I was going to present there, and I got canceled like a few days before. Right. Yeah, and so you know, I think that CERN is using a model of standard physics. The standard model of particle physics that's inequated, that is actually only consistent within the model, but is inconsistent when applied to the universe. And one of the inconsistencies that the Higgs mechanism only predicts 1 to 5% the mass of the proton, which in my case, the equations predict 100% of it. The rest, they use lattice QCD, which is not an analytical solution, which costs millions, and in some cases billions of dollars to run supercomputers to solve the equations. It can take months, if not years, to solve these equations with supercomputers because they're not analytical, right? They don't have a good conceptual understanding where mass come from for these particles, and the mass of these particles make up the mass of our universe, make up the mass of everything we see. And so, and remember that E equals mc squared, so mass is equivalent to energy. So that means we don't really know where energy comes from neither. And like I was saying with this oscillator, when you zero out the 0 point, you got, so quantum mechanics became like magic, right? And when I say that, it bums out a lot of people that are more spiritual, because you're like, oh, but you're taking the magic away. And and especially when I tell them that the Copenhagen interpretation of quantum mechanics is wrong, like it's not like when you observe it that the cat becomes alive or dead.
You don't have only friends.
No, no, I'm not making friends on that side, and I'm not making friends on the physics side. It's problematic because when you make a philosophical interpretation of quantum mechanics to, for instance, try to understand consciousness, because you say, oh, because there's another part of quantum mechanics that says, well, when you make a measurement is when the universe like collapses, it's called the collapse of the wave function, and collapses into the reality you observe, like randomly collapses. And so this, and this interpretation, Schrödinger, which wrote these equations, thought that that interpretation was wrong and ridiculous, and that's why he came up with the Schrödinger cat, right? The idea that if you have a cat in a box and there's a little vial of poison and there's a hammer that could fall on the vial or not fall randomly, the cat is in both states of alive and dead at the same time until you make a measurement. But this interpretation of the double slit experiment is really a fallacy, because he made that example to make fun of it, because he was saying this is wrong, not because he was saying, oh, this is a great, analogy to describe quantum mechanics. He was just trying to explain this has got to be wrong. The cat cannot be alive and dead at the same time. And what do you mean by measurement? What about the flea that's on the cat? What is it measuring, a live or a dead cat? Or what about the microbes in the box, right? All these other frame of reference have to have some meaning in the universe.
Yes.
And so how do you resolve that? Well, that was resolved by de Broglie at the time, French physicist that did really good work on this, with eventually David Bohm, which did really good work on this as well, and got really chastised for publishing on this, to the point that he exiled himself to South America. But there's the Bohmian mechanics is a much closer approach, and Bohmian mechanics tells you basically when the particle is moving to, the double slit experiment, right? You have one slit, you're sending particles at it, you get little dots on the backboard. You get two slits, you send particles, you get interference on the backboard where you would expect dots on both slits. And so then it's like, oh, interference, they must be waveforms. So the particle is a particle and a wave at the same time, and your brain start to dislocate, right? I mean, I don't know what they were smoking in Copenhagen, but, it was not really a good interpretation. And then they tried to measure which slit is the particle going through. And when they tried to measure, they got the dots back on the backboard. And they said, oh, wow, when we measure, it collapses into its state. And that eventually became the way we wrote the math. Okay, but you can write the math in a completely different way with Bohmian mechanics, in which you're saying when the particle is moving, it's in a field. The field is not empty, right? Now, Bohmian mechanics kept it into a probability field. I'm generalizing that to more like literally a fluid dynamic field of the zero-point energy, right? And so when the particle moves in that field, it makes waves. Right? So it's a particle and a wave, but not in some weird esoteric way. It's a particle and a wave because when an object moves in the field, it makes waves. Like a boat on the ocean makes waves. And it's a boat and a wave. If you're observing it from far, you would say it's a particle and it's making waves. And then the waves go through the second slit. And all this was proven at MIT and other universities in France as well, where they used silicone fluid and little beads and shot them at double slit experiment. They got all the right results. And what happened is when you go to measure, the thing you're using to measure, it's making waves too. So it's interfering with the waves that the particle is making, and now you get a third result. And so, and so it removes like the weirdness of quantum mechanics. It tells you there's a field, and that field was found by Max Planck. It's called zero-point energy. The uncertainty of Heisenberg is not the cause of the oscillation of the field. It's the oscillation of the field that makes it so you can't pinpoint the particle because it's oscillating in a field, right? You see all of a sudden everything becomes clear, and you're dealing with like fluid dynamics of a field. And when I say that to the more spiritual people, the people that are talking or studying consciousness, they could be physicists. In some ways, it's like I'm taking the magic away. And they don't like that, but it's putting actually the correct mechanics in, and all of a sudden there's a whole other kind of magic that's...
It opens another door.
It opens another door,
Wow.
a much deeper door. That like you and I were bathing in a field that is interacting with us, and that is, it's much more fundamental.
Yeah.
That like you cannot be isolated from that field, and that field cannot be isolated from anything. And in fact, in the paper we wrote, we show that that field is the source of mass, that is the source of particles. There's no particle and field. There's just a field that makes a particle when it makes eddy currents, or like little eddies that are spinners that are very stable and that are producing particle. And that those particles is the material we see in the field. But the field is oscillating at frequencies that are way beyond what we like experience directly. Oh, we're talking, you know, Planck time 10 to the minus 43 second, 42 second, right? So it's very, very fast. You know, it's a frequency really, really high, right? That's the wavelength, right? And so basically you know, so that if you were like to take one of those little oscillation of the Planck and you made it so that it would be a grain of sand, right? Well, the proton would be from here to Alpha Centauri, right? Which is about 40 trillion kilometers or something, or, you know, 27 trillion miles or something like that. And so that would be the size of the proton if the Planck was a grain of sand. Wow. So imagine how many grains of sand you can put in a proton, right? If the proton is from here to Alpha Centauri in radius, right? And so that like gives you a sense why we don't feel this thing. But even long before that, we don't feel the electromagnetic field. We only experience with our body the electromagnetic field in a very short, you know, part of the electromagnetic spectrum, right? Like there's radio waves between us, there's microwaves, there's background radiation from the galaxy, there's background radiation from the Big Bang.
Solar flares.
There's solar flares, there's all kinds of stuff between you and me right now. We have no idea, right? Until we have a little device that taps into it, and now we hear the radio, or we use our cell phone. So basically, this field is present at the source of creation, and the paper I published didn't just show that it's a source of mass, but literally, and it's beautiful the way the equation is. It's mind-boggling. And the next paper on that side of the physics that's coming
that's the
out,
one you're publishing on consciousness.
No. The one I'm publishing on consciousness is
coming up soon.
And
there's another one.
There will be, and there's another one that's coming up soon as well on the hard physics, and you know it solves. So the way we solved it in the one I just published is that we showed that
a year ago.
Yeah, a year ago, we showed that like, okay, so you take the proton and you take all the modes of oscillation of the 0 point in it. Okay, and you calculate how many modes of oscillation all the way down to the Planck size, to the smallest, inside the oscillator, right? Because now you didn't remove the source of oscillation of the oscillator.
Yeah,
you have it in,
whole, yeah.
So now you have it in there. So you calculate, and you imagine the waves are bouncing all around, and some of them are canceling out, and some of them are building up energy, right? And so we calculated that. It's called the correlation functions equation. And when we calculated the amount that are canceling out, most of them are canceling out, but some of them are building energy, right? Because they're constructive.
To which factor? So how much, so the percentage of them that are actually building up?
Yeah, the percentage of them that are building up. So how many are not canceling out, right? And we got the exact mass of the proton. Exact mass we measure, right? Which is remarkable.
Yeah.
And in the next paper, actually, we show that the ratio of the ones that are canceling out to the ones that are building up, that are creating energy, that ratio is very, very special, but I'm going to keep it for the paper, okay? It's very, very special, but it's remarkable. But basically, it gives the correct answer, and then we calculated how much pressure it would produce inside the proton, this energy, and we got the pressure that they're measuring that's inside the proton, which is similar to the pressure of a neutron star. It's like really high pressure, and it's called the color force. It's the force that is at the source of like the confinement of the protons together in the nuclei. And we got the right answer. So we have the Planck force, then it gives the color force in the proton, then it as you get away from the proton, it drops again, and it gives the residual strong force, which is the nuclear force that holds the nuclei together. And then you keep going further from the proton, and approximately 2.6 protons away, it becomes the gravitational force. So we showed that it's all the same force. That it's all the same force, and what Einstein called space-time is just the fluid dynamics of the 0 point energy. It's remarkable.
It must be so satisfying.
It's unbelievable. It was unbelievable. It came out so sweet, so clear. And it was like, wow, that's just amazing. And we published it in a certain way, in pre-published format. The final published paper is actually much more explicit on how we make the calculation for the forces and the pressure. And we basically solve Einstein field equation and show it's equivalent to what we found. So it's actually bomb-proof, solid. And
what's coming out of that when it's published?
Yeah, I mean, so that's gravity, the strong force, and the electromagnetic field, which includes the weak force, unified, you know, and...
et voilà?
Yeah, et voilà. and you know, I think I'm at 66,000 downloads of the paper, which is a lot for a 50-page physics paper full of equation. It's not the kind of things that you download, you know, to have light reading before bed, you know, it's...
But the next ones are going to be even bigger.
Yeah. The next one are bigger.
More impacts. I mean, just this wraps it around.
That's right.
This was
just the first little teaser. The rest is coming. We've solved everything, like incredible amount of stuff behind.
So when you say we, what's the team?
It's Dr. Olivier Alérol and Dr. Cyprien Guermontret, and you know, and these guys come from the best schools in France and in England, because Cyprien did his master's in Cambridge. But you know, it's
this is more than 35 years of research for you.
And it's 35 years of research, culminating with these guys helping me. I mean, those guys are amazing. And there's so many amazing physicists in the schools right now, and they have nowhere to go because they were all directed towards string theory for decades, which ran right into a wall. And so, like...
But not all universities must be very happy of that, or...
No, of course. Yeah, it's... a lot of scientists are really looking at alternative theories now, and that's really good. I'm really glad. I'm happy about that. AI is helping. AI is helping a lot.
Good.
That's good because until recently, AI could not solve equations properly. It would solve properly a few equations and then go...
Yeah, tell us about that, yeah, how it's helping you. Yeah,
yeah, it was making large errors, and if you weren't, you know, very astute, yeah, you could get in trouble. But now it's becoming much more solid, so it's much easier for physicists to go through much more material much faster because you can give the papers to AI and query it, and then like ask it to give you more details on certain equations, and then verify.
So but all of that information then becomes public immediately as you're putting it in. It's not a private system.
No, it doesn't necessarily become public because AI is not necessarily learning from its queries, but
Sure.
Yeah, but it definitely is advancing the field faster. And I think people are becoming more and more clear about very obscure parts of quantum mechanics and of relativity that like were really difficult to comprehend. I think AI is really helping people get a really good, clear sense of what's solid and what's not so solid. Because, for instance, you know, part of quantum mechanics is acclaimed as the most precise theory ever, you know, written and ever discovered. And it's precise only in the sense that enough free parameters have been put in so that they can curve fit, right? It's not precise in the sense, so physicists always, especially professors, love to state that to their student. This is the most precise theory, da da da. It's precise only in the sense that you can tune the theory to give you the correct answer and then somewhat justify those tuning with measurements in accelerators, but a little bit circular. But actually, it's not precise in the sense that it tells you what is the mechanics of the universe. It's not precise at all to tell you that, because these solutions, QCD, QED, are non-analytical. They don't give an analytical solution. They don't tell you these are the mechanics that makes this happen. It just, as Feynman said, generally teachers say to the kids, shut up and calculate. Don't try to visualize it. Don't try to understand the mechanics. Just do the math, right? And so, you know, it became theoretical models that don't relate actually.
And they skewed consciousness.
And of course, they skewed consciousness because
which is a huge factor.
Well, which is a huge factor. How is consciousness even possible in the quantum universe? And it's not. Like, you know, the collapse of the wave function and the Schrodinger cat is completely random. There's no, like, consciousness involved at any point. And so this is another part that this new approach starts to solve. And that's what we're going to publish in this summer in relationship to a conference on consciousness from Stuart Ameroff and Roger Penrose that do a conference every year on consciousness or the physics of consciousness. And so we're going to present that paper, and that will come out. And in that paper, we show that from the Planck field, from the 0-point energy, we figured out how it couples, because remember how we solved for the proton? So the proton is big compared to the Planck, right? So as a result of solving for the proton, and then eventually we solve for the electron, which we have as well, and planets and stars and galaxies. And so we got the scaling, how the universe is scaling, you see? I know I'm not letting you ask many questions.
No, it's amazing.
Yeah, but I'm excited.
And so
about
what's going on exactly in the lab in France then?
I was going to finish with the consciousness. So when it's scaling, that means we can figure out how it, so like you have a certain level of energy, and then it couples to a higher scale, right? Because the smaller scale makes up the higher scale, and we can tell how many energy has been lost in this coupling, right, to make the proton, and then higher and higher and higher and higher. And so we did that for biology from the Planck scale. And we found, and so we applied the coupling constant, and we got carbons, right, the base of life. And then we got the benzene ring, right, which is the 6 carbon atom. And then we got, I'm going to skip some details, but we got like the tubulin, which is like the little thing that makes up the microtubules, right? And that Roger Penrose and Stuart Ameroff had come up with like these little tubes that are lasing, that are creating like a high energy physics inside the brain, might be the source of consciousness, like the antenna of consciousness. We show that it actually, so we get the right value. We get the right value for the carbon atom, the benzene ring, the tubulin, that are the little things that make the tubulars, and then the tubules, bundles, and then eventually to the neurons. And when we get to the neurons, we're getting all the right frequency for all these things, which are measurable things, right? And when we get to the brain, we get like 30 Hertz approximately. We find the typical, frequency of the brain. We've scaled from the Planck scale, which is like, extremely small. And so we show that like it's all like the energy or the information of the Planck field that's in a feedback relationship with our biology that organizes biology all the way through, and eventually that feedback becomes what I believe we call consciousness. So it's like the Planck field, like we're like probes of the Planck field experiencing the universe or experiencing ourselves, because everything else is made of the same.
But then that's a great way for people that are, it's great information for spiritual people too, because then that means we can access even further to and tap into this immense source of wisdom and of energy.
Exactly.
With our bodies.
Exactly.
Physically.
We
haven't talked about water, but that's going to be an important topic soon. And and that's something already that we have talked about through the art crystal, restructuring the body of the water of the body. And restructuring us for us to be more in coherence with the universe, let's say, and us being more hydrated, let's say. But I guess that with all of that, that's gonna through the water and through other technologies. It's interesting to know where you're at with that, so that we can even further connect and receive and reveal our own potential as human species.
It's remarkable, and like there's so much more physics to be written, especially biophysics in that field. And like, I would so love to have more resources, to have more physicists and more, working on it. But
it will come.
It will come, and it really surprised me how clean that was. It really surprised me. It was not obvious that would give the right answer, and that when we would get to the neuron, which is like way far from the Planck scale, that we would get the right frequency.
You got some help from another timeline, let me tell you.
I know.
It's a lot of hard work too, but
it just blows my mind how beautiful the universe is.
Yeah.
You know, it blows my mind how beautifully organized, like how perfectly synchronized. It's mind-boggling. And
so good to hear from a physicist.
yes. Well, I actually wrote it at the end of the paper I published a year ago. I wrote, in my acknowledgement, I wanted to acknowledge the universe for its mathematical beauty. And when I said mathematical beauty, I didn't mean it in pure math, because I actually don't believe the universe is mathematical. A lot of physicists say that. Mathematics is the language we use.
Like a partition, I see notes when you see that in music instead.
Right. But it's not the music.
Yeah.
It's just the writing we use to describe the music.
Yeah.
The music, I think, for the universe is geometry, is ratios, is relationship. It's relationship of all things. Interconnected. It's so profound. And it's so remarkable that you can actually write the math for it and it will come out. And understand that geometry. And then all of a sudden it opens the door to like fantastic transformative technologies and understanding of ourselves, understanding of the universe and our relationship to it. Like a whole new world emerges because you've understood that you're interacting with the field. Really, that's the main thing. And so yeah, in the laboratory in France, we are working diligently on.
It's called International Space Federation now, right?
Right.
It has changed names.
It has changed names.
It's not anymore Resonance.
Yeah, Resonance Science Foundation and Torres Tech, which was my laboratory in California, have now come under ISF, International Space Federation, where we're, working on energy production from zero-point energy and gravity control, because it leads directly. That is the goal of ISF is gravity control. There is steps towards that, and one of those steps is extraction of energy. And that's coming from many laboratories around the world. It's emerging right now, and people should know that. They should know there's a solution that we can really transform this world, and we can become completely or very, very strongly coherent with the natural world instead of destructive to the natural world. And so that,
So when can we expect that to be the case for everyday people?
Well, I think now it's imminent. In the next year and a half to 2 years, it's imminent. There's other labs. For instance, there's a lab in Italy that just got funded very well that has a technology of low energy nuclear reaction. So what was used to be called cold fusion and supposedly got debunked. This became so an Italian engineer has solved it and has a little device that's producing a little bit of energy, and he put it in a car, and the car can go without charge, and so on. And so he's in the middle of production, and it might come out. Now, he's been on it for a long time. 2012, he had some difficulties. So, it's on its way. There's I remember back then interviewing Foster Gamble back in when Thrive came out, and he was saying, imagine a concert, and all of a sudden we show that there is just nothing that is making, he was imagining without the lights and
everything on and coming from free energy.
Right, and that's on the way.
Yeah,
it's on the way. People say, why is it taking so long?
Yeah.
Well, you know,
You have to do it well.
well, first, zero-point energy got a bad rap for a long time. Many people thought that zero-point energy, even the terminology, came from some inventors in a garage. It's the basis of quantum mechanics. But as well, so most of the research on zero-point energy was never financed. So laboratories are expensive.
Yeah, you're a miracle. I remember back then when Princesse Constance de Polignac, you know, there was the movie that came out, The Connected Universe, and we did the premiere in Paris.
Yes.
Like what, 10 years ago?
Yeah.
Where was that?
And
she was there, she was financing. I mean, there's some people from all around the world.
All around the world.
Private funds and always more coming if you can.
Right.
Right? That's part of the...
Critical.
C'est
critical.
If you can.
Think of CERN. The CERN receives, I think, it costs about $1.2, $1.5 billion a year to run the accelerator. You know, with like 1%, we would like, you know, so it really, people are asking, why is it taking so long? Well, because it hasn't been properly financed.
Yeah.
But it's coming out
happening.
now.
Yeah.
It's happening.
Yeah.
It's happening, and I think the scientific community, or at least the impact investors, are starting to get that is the place to go.
Yeah.
And like that's so critical, because basically Tesla was there, the Mori brothers were there, Sparky was there. I can't remember his full name, but you know, there was many devices, and but they never got the correct support, right? And so this is where we're at, and you know, it's remarkable. For instance, what happened with all the UAPs in the U.S. You know, now, like in about a year and a half, 2 years, it went from, if you talked about flying objects in our airspace, people thought you were a little, you know, cuckoo, to now it's like Congress and the top scientists and the top, you know, military industrial complex.
Because the technology they're using is that.
Well, there's definitely projects that have been working in the background in all these certain institutions that have been working on this. And so there's a podcast, maybe we'll put it as a link as well. Yeah. You know, there's a podcast where military and like DOD and DOE and all these people are being interviewed about zero-point energy and talking about it very openly, talking about research on gravity control very openly, how long it's been going on and what they've succeeded in achieving, or at least what has been declassified and all this, and in a very serious way, and calling out to the financial, you know, private industry to like finance this type of research and get it out. And so it's really kind of coming out at the seam.
It cannot not be.
Exactly. It's a fact. And most scientists, unless, you know, they're like living in a cave, or, you know, it's a fact, there's flying objects in our airspace that are defying the currently known laws of physics. They're not breaking the laws of physics, they're just breaking the laws of the human physics, right? Yeah. They're actually not breaking the laws of physics at all. They're utilizing the laws of physics. It's just we've made a little bit of an error in our laws. We've eliminated what used to be called the ether, the energy of the field. And so if you don't have the source of energy, then you know, you're not gonna know that you can have a lot of energy if you want to, and you can curve space-time. You can do things that you couldn't imagine doing, just as much as, you know, before the Wright brothers, you couldn't imagine, and there was hundreds of papers published in the scientific journals that said it was not possible for anything heavier than air to produce enough lift to lift itself, because that sounded like free energy, right? That sounded like you're violating the laws of motion, because it's like you have a motor that weighs, you know, hundreds of pounds or tons or kilos, you know, like hundreds, thousands of kilos that are lifting their own weight off the ground with the wind that it's producing, right? That didn't sound possible. That was impossible. And there was hundreds of papers published proving mathematically that it was not going to happen. And until two Wright brothers in their bicycle shop, right, got a bunch of motors and chains and bicycle wheels and stuff going, and they got off the ground. And you know, it was literally barbed wire and duct tape. They didn't even have duct tape, you know, and they got it off the ground, and from one day to the other, although it took 10 years in Europe before they stopped publishing papers saying that it was a hoax, you know, it took humanity from being stuck to the surface to not even thinking twice about it, getting on a thing that weighs thousands of tons, right? And flying through the air and going to the other side of the world and just doing it without really thinking about it, right? Well, gravity control is just the next step of that, right?
So what's your next step? I was going to ask you, but where you're at with that now, where are you taking?
Right.
There's something else that you're excited about?
Oh, yeah.
Kind of like, oh my God, this is it. I mean, I've done my job. Forget it.
I'm excited to. This
is where I wanted to be. Now I'm done.
Well,
I'm going to retire in Morocco or in the sun. I don't know.
I'm definitely excited to not be working 7 days a week and, like, you know, having accomplish what I want to accomplish and being able to go surf and ski a little more and spend more time with my kids. But I think that I'm actually excited to, like, see the world transform.
You want to see that?
Yeah. And to, like, so many people stop me in the street and, you know, tell me, you know, that you changed my life, and, like, I listened to you, and, like, I got a completely different perspective on life, and you know, I think at the time it was less rigorous. Now it's more rigorous and much more rigorous, but for people to be able to see that light come on behind their eyes when they get the sense, oh my God, I'm interacting with the field, I'm part of something bigger, you know, I'm not isolated. You know, I want to start a podcast called, my staff doesn't like it, but I really wanted to call it that way, so I'm going to have to push it through. But I want to call it Out of the Box, because they say, oh, it's a known expression and all. But I want to call it Out of the Box because I want to make an analogy that you can't have anything in the box. The box, you can't have a box.
You should call it Out of the Oscillator.
Yes.
There can be another, little bit more, instead of box, it could be another name.
Right. Out of the...
But we want you on air, for sure.
Yeah, well, you know, I because I want to comment, because there's a lot of podcasts that are very popular, right? Like millions and millions of views, that are discussing physics from the standard perspective, and, you know, that explore a little bit here and there other perspective like Bohmian mechanics and all this. But and, you know, I just feel like they're, you know, when they're describing these things, they're missing just this little bit that if it was put in the right order. People ask me all the time, how do you come up with this? And I say, I didn't come up with anything. I just looked at what was already there and I put it in the correct order, right? And when you do, then it becomes obvious, right? It's like, well, you know, the theories of Einstein predicts wormholes, right? It actually doesn't really predict anything else than black holes and wormholes. And when you apply it to the proton, you get the right force, right? And you know, so basically, like black holes and protons are the same thing at different scales. And that's why protons are like crazy things that are continue isolating, you know. And so basically, you know, it's just changing the order of things. And it's because historically it was found in different orders, and because there was some censor of certain information which might have been legitimate at the time to do, but not anymore.
Brilliant. Thank you, Nassim. Thank you so much
you.
for this time and taking the time to come here to
It's
Paris.
always great talking with you, although I did most of the talking. I'm sorry.
That's why you're here.
Yeah, I just get excited about these things.
Yeah, but this is what we love. I remember the conferences that we organized for you. It was like 4-hour conference, and we had to stop you eventually.
Yeah,
and we
pull me off the stage.
And then you're still talking to the people. Like, Nassim, what are you doing? I mean, literally, the thing is closing. You're shut off the lights. I mean, you're passionate. We love that about you.
I appreciate.
Amazing human being. Thank you.
I appreciate, and I really look forward to like discussing for people that are technical in more technical terms, everything. Like contact us, let us know. You know, it's spacefed.com is ISF.
I'll put all these links under the video. For
awesome.
Sure.
Yeah, talk
in French
to us.
and in English, it's going to be translated to in French, and it can be translated now with AI in multi-language, I think, at some point.
Yeah, exactly. And, you know, even use AI to query about the research I've been doing and all this. In general, it's fairly accurate. You know, it still says, you know, it's not the mainstream view, and that's normal. It is not.
But wait that the paper will be updated soon.
Right, exactly.
Thank you, Nassim.
Thank you so much.
Thank you so much, and thank you to all your team, because I know you're well surrounded now.
Thank you.
And you went through so many different phases.
They're amazing.
And you have rebirthed it so well done, because I know what you went through. I mean, parts of it. And
right.
This is what makes it possible too. The chaos is part of the whole equation as well.
Exactly.
Isn't it?
It's
you have to go through that for a human being to evolve.
To bring a new level of order.
Yeah.
Yeah.
Brilliant. Thank you so much. Please share abundantly to all the people around you this video. Please subscribe to this video. I'll be putting more and more to this channel. I'll be putting more and more videos in English now. And so it's really good to be back. Much love, big kisses, love you guys.
Thank you.
Thank you, Nassim.